Nearly every machine in use today has one thing in common. They all experience a certain amount of vibration. According to the formal definition, vibration is the periodic motion of a body or medium in alternately opposite directions. In simple terms, vibration can be thought of as the back and forth movement of a rigid object. In some cases, vibration is a normal part of a machine's operation. In other cases, it can be an indication of a problem. Whether the vibration experienced by a machine is normal or abnormal, it is capable of causing damage. Because of that danger, some machines are equipped with built-in vibration monitoring devices. For example, the engines on this aircraft are equipped with devices that monitor vibration and relay information to the pilot concerning the engine's performance. Other machinery, such as the equipment found in your plant, may or may not have built-in vibration monitors. On the machinery that doesn't have these built-in devices, it may be your responsibility to measure vibration levels and either analyze the data yourself or provide it to other personnel. To do either job properly, you'll need to understand how vibration works and how it can be measured. During this program, we'll spend some time examining vibration. We'll identify some common terms associated with vibration, and we'll look at some of the things that cause vibration in different types of machinery, primarily machines with rotating components. We'll also look at some instruments used to detect vibration. Then, a little later in the program, we'll look at some guidelines to follow when collecting vibration data. Let's begin by looking at how vibration works. Basically, there are two types of vibration. One is called free vibration, and the other is called forced vibration. Free vibration occurs when a single force is applied to an object, and the object is free to move until it stops. For example, when a tuning fork is struck one time, it vibrates until it stops on its own. Forced vibration occurs when a force is applied repeatedly to an object. For example, on this clock, the clapper strikes the bells repeatedly, causing them to vibrate continuously. We can get a better understanding of the characteristics of a vibrating object by using this block and spring. To illustrate free vibration, a single downward force is applied to the top of the block. As the block moves upward, it gathers speed and passes beyond its original position. As the spring is stretched again, the block slows down, comes to a stop, and starts upward again. Then the compressed spring resists the upward movement of the block. The spring then pushes the block back down, where it again gathers speed and passes by its original position. The process repeats itself until the block eventually stops moving on its own. That's because the block and spring are not operating under perfect conditions. The dampening properties of the spring decrease the block's movement. As a result, the block travels less distance each time until it finally stops moving and rests at its original position. Now, in a forced vibration situation, a force is applied repeatedly to an object, and the object moves about the same amount each time. We can use the same block and spring to illustrate forced vibration. In this situation, the downward force that starts the motion of the block is repeated each time the block returns to its original position. As a result, the block travels about the same distance each time, and it will continue to travel the same distance unless something happens to change it. Forced vibration can be caused by an internal or an external force. Since the force is repetitive, it resembles the type of vibration most often found in the machinery in your plant. We'll take a closer look at this type of vibration and its causes a little later when we look at vibration in rotating equipment. Now, the examples that we just saw may appear to be quite different from the machinery in your plant, but in reality, whether the vibrating object is a block and spring or a centrifugal pump, the actual movement that takes place is basically the same. To understand this, we simply have to define certain terms that are associated with vibration. For example, one term that's used in describing vibration is cycle. When the block moves from the starting position to one extreme, then past its starting position to the other extreme, and finally back to its original position, it is said to have completed one cycle. The number of cycles that occurs over a specific amount of time is known as the frequency of the vibration. Frequency is one of the fundamental characteristics of vibration. Frequency can be measured in cycles per minute, which is abbreviated CPM, or in cycles per second, abbreviated CPS. Cycles per second is simply cycles per minute divided by 60. Cycles per second can also be expressed as Hertz, named after the 19th century German physicist Heinrich Rudolf Hertz. If we apply this information to the block and spring that we just saw, we can determine the frequency of the block's vibration. Let's say the block completed 1,200 cycles in 1 minute. If that's the case, then the frequency of vibration would be 1,200 cycles per minute, which can be converted to 20 cycles per second, or 20 hertz. Another term used to describe certain features of vibration is displacement. Displacement is the distance between the two extremes traveled by the vibrating object. Displacement is usually measured in mils, which is 1/1000th of an inch. For example, when the block in the model moves up and down, it travels between two extremes, from here to here. By measuring the distance between those 2 points, the amount of displacement can be found. For instance, if the distance between the two extremes measured 20/1000ths of an inch, then the displacement would be 20 mils. Sometimes displacement is referred to as a peak-to-peak measurement. That's because the 2 points from which the displacement is measured, seen here as the highest point and the lowest point, can be thought of as peaks. Another term that's associated with vibration is velocity. Velocity is a measurement of the distance that an object travels in a given period of time. The velocity of a vibration is normally measured in inches per second. For example, if the block travels 1 mil in approximately 1 second, then the velocity of the block is 1 mil divided by 1 second, or 1/1000th of an inch per second. The velocity of a vibration is constantly changing. For example, the velocity of the block is faster as it passes by its original position than it is when it reaches one of the extremes. Because of that, velocity is sometimes measured when it's at its highest, which is known as peak velocity. There's another term that's often used to describe certain aspects of vibration. That term is acceleration. Acceleration is a measure of how fast an object changes speed. Acceleration is often expressed in inches per second squared. Inches per second squared means that an object's velocity increases at a certain number of inches per second for every second that passes. For example, suppose the block travels downward from here to here. As it moves, its speed increases or accelerates. So let's say that in the first second the block travels 2 inches. Then, in the next second, it travels 4 inches. And in the next second, it travels 6 inches. We can then say that the block was traveling an additional 2 inches for every second that passed. In other words, the block was accelerating at a rate of 2 inches per second, or 2 inches per second squared. Another way that acceleration can be expressed is in g's. A g is a rate of acceleration equal to that which is caused by the force of gravity. Gravity causes a falling object to accelerate at a rate of 32 feet per second squared. So 1 g equals 32 feet per second squared, or 384 inches per second squared. There is a relationship between acceleration and velocity. When acceleration is highest, velocity is lowest. And when acceleration is lowest, velocity is highest. This child on a swing can be used to help illustrate how acceleration and velocity are related. If the child has just reached one peak and is starting to move in the opposite direction, then acceleration is at its highest, while velocity is at its lowest. Likewise, if the child is traveling through the original starting position, which is midway between the two peaks, then velocity is at its highest, while acceleration is at its lowest. As long as the child is moving, velocity and acceleration are constantly changing. This action is basically the same for vibrating objects. Another term associated with vibration is phase. Phase is the position of a vibrating component in reference to a fixed point at a specific time. For example, the block shown here travels past this fixed point. So regardless of where the block is located, its position can always be compared to the fixed reference point. By measuring the phase, the movement of the block can be better understood. Now, one more term that's often used in vibration analysis is amplitude. Amplitude is a general term used to describe how much displacement, velocity, or acceleration exists. Now, we've looked at some of the terms used to describe vibration. Three of these terms, displacement, velocity, and acceleration, represent parameters that can often be chosen when monitoring vibration. In other words, in most cases, you can choose whether to measure the displacement, velocity, or acceleration of a vibration. Deciding which parameter to choose could depend on the information you hope to get and on the frequency of the vibration being monitored. For example, a good rule of thumb concerning vibration monitoring is that if the frequency of vibration is between 0 and 600 cycles per minute, then the most accurate information can be obtained by measuring displacement. If the frequency is between 600 and 60,000 cycles per minute, velocity should be chosen. And if the frequency is above 60,000 cycles per minute, measuring acceleration will give the most accurate results. Well, we've seen that nearly every type of equipment experiences some sort of vibration. By measuring and analyzing vibration, a great deal can be told about a machine's condition. As we continue our examination of vibration, you'll be able to understand more about how the information we've seen so far relates to the equipment in your plant. When we come back, we'll start applying some of this information to rotating equipment. Then, a little later, we'll see how vibration is measured and how the data gathered from those measurements can help identify certain problems. We'll also see how charts can be established to indicate whether a trend exists. But first, read the first section of the text and answer the questions at the end. Many machines with rotating components often experience vibration problems. Since the vibration found in these machines is still basically a back and forth motion, the effect is similar to what we saw in our earlier examples. However, there are differences as well. For example, machinery vibration generally moves in all directions, rather than simply up and down like the block and spring we saw earlier. In addition, the amount of movement or displacement is usually quite low. But even though the movements are more complex, they can still be described by using the terms that we defined earlier. As you recall, the frequency of vibration is the number of cycles that occurs over a certain period of time. To understand how this relates to rotating equipment, we have to understand a little about the nature of the components themselves. For example, all objects have a frequency at which they like to vibrate. This specific frequency is called the object's natural frequency. The natural frequency for this pump impeller is different from other impellers, or from other objects for that matter. When the impeller is struck, it vibrates at a specific frequency until it stops. The natural frequency for an object depends on many things, such as the object's shape and size. Besides having its own natural frequency, a rotating component may also experience vibration equal to its rotating speed. The frequency of this vibration is known as rotational frequency. Vibration peaks caused by problems such as misalignment and imbalance commonly occur at the rotational frequency. For example, suppose this impeller is out of balance. If the impeller is rotating at 3,600 RPMs, then the imbalance could cause the impeller to vibrate at the same frequency. In other words, the rotational frequency for the impeller would be 3,600 cycles per minute. A separate rotational frequency exists for each rotating part in a machine. This gearbox, for instance, has 3 shafts, and each shaft rotates at a different speed. As a result, there are 3 different rotational frequencies. When a component rotates so that its rotational frequency equals its natural frequency, the component is said to be operating at its critical speed. At this critical speed, the rotating component is most vulnerable to damage caused by problems. If the component is perfectly balanced and aligned and has no other problems, then it may operate normally. However, if a problem exists and the component is allowed to operate at this speed, the severity of the vibration could damage or destroy the component or other components. This increased level of vibration is known as a resonance. For example, suppose the natural frequency of this shaft is 6,000 cycles per minute. If the shaft has an alignment or balance problem and is allowed to rotate at 6,000 RPMs, the vibration could become so severe that it could damage the shaft or other components. On some machinery, the operating speed cannot be controlled. In these cases, the machinery is normally designed to operate at speeds greater than or less than the critical speeds of its components. On machinery where the operating speed can be controlled, safe speeds are normally specified by the manufacturer. In addition, operators are usually taught to avoid operating rotating equipment near its critical speed. Some equipment has more than one critical speed because of the number of rotating components present. For example, a single rotating shaft might have many impellers and collars. Each component would have its own natural frequency and critical speed, so it would be dangerous to operate the machine at any of the critical speeds. For the operator's benefit, some types of rotating equipment have tachometers that show the critical speeds for that particular machine. In addition, owner's manuals may also list these speeds. Now that we've seen a little about the nature of rotating components, let's look at some of the causes of vibration in rotating equipment, and there are quite a few. In most cases, vibration in rotating equipment is caused by problems with rotating components. When a rotating part is damaged, the abnormal forces that are generated occur repeatedly. As a result, the machine undergoes forced vibration. By analyzing the vibration with vibration monitoring equipment, many of the causes can be identified with relative ease. One of the most common causes of vibration in rotating equipment is an imbalanced rotating element. A rotating element becomes imbalanced when its weight is not properly centered around the axis on which it rotates. The imbalance could be caused by a manufacturing error, wear, or physical damage. For example, a rotating shaft may become out of balance because of abnormal wear. One way to check the vibration that results from an out-of-balance shaft is by measuring its phase. Phase can be measured using a strobe light that's connected to vibration analyzing equipment. The vibration equipment will cause the strobe light to fire once during each revolution. When the strobe light flashes, keyways, couplings, and marks on the shaft will appear to be stationary. One of these marks on the shaft is chosen to compare with a fixed point on the stationary part of the machine. The angle between the chosen mark and the stationary point is called the phase angle. The phase angle is used in conjunction with the amplitude of the vibration to balance the rotating equipment. Balancing the rotating equipment generally involves adding trial weights to the rotating element. Then, when the element is rotated, the phase angle and the amplitude of the vibration changes. These changes can then be used to adjust the weight so that the rotating element will be balanced. Now, an actual balancing procedure is a little more complicated than the simplified version that we just saw. Special training may be necessary to do the job correctly, and that's beyond the scope of this program. The point is, vibration in rotating equipment can be caused by many types of problems. Let's look at some other examples. Another common cause of vibration in rotating machinery is shaft misalignment. A small amount of misalignment between shafts can put additional stresses on the shaft and its bearings. These additional stresses produce their own distinct vibration. Vibration caused by misalignment can occur even when flexible couplings and self-aligning bearings are used. The only way to correct this condition is to align the shafts until they're within the manufacturer's specifications. Many vibrations can be traced to loose bolts or other parts. In most cases, these parts simply need to be tightened or replaced. Damaged or worn bearings can also cause vibration in rotating equipment by not allowing the shaft to rotate properly. Both sleeve-type bearings and rolling contact bearings produce distinct vibration frequencies as they wear or fail. With the proper vibration monitoring equipment, machinery equipped with roller bearings can be tested to determine if the problem is being caused by one particular part of the bearing, such as one of the rollers. We've just seen some of the more common causes of vibration in rotating machinery, but sometimes vibrations are detected that can't be attributed to any of the causes that we just saw. In these cases, other possible causes must be investigated. For example, vibration could be caused by a shaft that's bent or out of round. The effect of a bent shaft is similar to that of a misaligned shaft. The oblong or eccentric motion of the shaft places additional stress on the bearings and other components. The additional stress causes vibration. Sometimes journal bearings are not properly aligned with the shaft that they're supporting. As a result, they wear in an oblong manner. When the shaft rotates in the oblong area of wear, instead of in the normal circular pattern, vibration can result. Vibration can also result from defective gear teeth. Generally, when a gear's teeth become worn or broken, it can no longer mesh smoothly with other gears. In many cases, the rough meshing action produces a distinct vibration. Loose or damaged drive belts can cause vibration in belt-driven equipment. For example, if a belt has a cut in it, the cut could strike the pulleys on each revolution and cause vibration. Electrical faults in a motor or generator may cause a break in the unit's magnetic field, causing the motor or generator to run rough. This can also cause vibration. Sometimes vibration occurs when the fluid flow near a fan or impeller is disrupted by a stationary object in the flow path. A condition called oil whirl can develop when the liquid surrounding a bearing or a mechanical seal starts to spin with the shaft. The spinning liquid can move the shaft and cause vibration. Sometimes vibration occurs because of a condition that's unique to a specific piece of equipment. For example, if there's contact between a rotating component and a stationary component in a machine, there may be a specific vibration associated only with that particular contact. Pumps can also experience vibration caused by cavitation. Cavitation, that is, the formation and collapse of vapor bubbles in a pump, can also damage rotating components in different ways. Whether the vibration is unique to a particular situation or general in nature, monitoring and analyzing the vibration could help locate a problem before it's too late. By detecting problems before they become severe, plant personnel can plan equipment repairs. When we return, we'll take a look at some of the devices used to detect vibration. Vibration can appear in a number of ways. Sometimes it can be seen. Sometimes it can be felt. And at other times, when it causes the surrounding air to vibrate, it can even be heard. But in many cases, vibration is hardly noticeable. However, just because vibration can't be seen or felt doesn't mean that it can't cause severe damage to the equipment. In order to monitor these types of vibration, some sort of vibration detecting device is necessary. There are many types of vibration detection instruments available. It's difficult to categorize them because of all the different features that are available, and because manufacturers use similar terms to describe different types of equipment. However, for the sake of our discussion, we'll group these instruments in three basic categories: vibration meters, which normally provide only overall displacement, velocity, or acceleration meter readings; vibration analyzers, which are generally a little more sophisticated than meters and can monitor specific frequencies so that a detailed analysis can be performed; and vibration monitors, which are normally permanently mounted instruments that are used as a visual indicator and a safety instrument. Vibration monitors are not normally used for vibration analysis. All meters, analyzers, and monitors use the same basic components to detect vibration. Those components are known as vibration detectors. These detectors are usually called pickup devices, or simply pickups. Pickups can be grouped into two basic categories: non-contact pickups and contact pickups. Non-contact pickups, which are also known as proximity probes, are normally used to monitor the motion of a rotating shaft. They're usually mounted in a bearing shell or casing so that the probe is nearly touching the shaft. When the shaft rotates, an electrical signal is generated by the proximity probe. That signal is usually fed to an instrument that provides a visual indication of the shaft's movement for operating and maintenance personnel. The pickup may also provide input to an automatic system that protects the machine from excessive vibration. The other type of detector, a contact pickup, is more portable in nature. The contact pickup, which is also known as a transducer, is attached directly onto the component that is to be monitored. Once the transducer is in place, it can detect the amount of displacement, velocity, and acceleration that the component is experiencing. There are several different types of contact pickups available. Two of the most common types are velocity pickups and accelerometers. Velocity pickups consist of a fine coil of wire surrounded by a magnet. The magnet attaches to the component being monitored and vibrates at the same rate. The coil of wire, which is suspended by springs that dampen the vibration, remains relatively stationary. As the magnet vibrates, an electrical signal is created in the coil. This signal is then transmitted to a device where it is electronically interpreted as a measurement of velocity or displacement. Accelerometers work on a different principle. They have a small crystal located inside a casing. When the accelerometer is attached to a vibrating machine, the crystal also vibrates and produces an electrical signal. As with the velocity pickup, this signal is then sent to an electronic device where it's interpreted as displacement, velocity, or acceleration. Accelerometers are normally smaller and lighter than velocity pickups. Because of this, accelerometers are often used on smaller components where the amount of vibration would be affected by the size and weight of a velocity pickup. Since contact pickups can be moved from component to component during vibration testing, they must be mounted properly to ensure that the information they provide is accurate. This includes how the contact pickup is attached to the machine that it's monitoring and where the pickup is positioned. For example, the pickup should always be attached to a clean, smooth surface that is free of any material that could interfere with the contact between the pickup and the machine. In addition, many pickup manufacturers recommend using a silicone grease between the pickup and the machine being checked. This helps fill any gaps between the pickup and the surface of the machine to ensure that there is a large area of contact between the two. It also prevents the pickup from chattering on the surface of the machine. There are a variety of ways to mount pickups. Determining which method to use could depend on the type of machine being checked. For example, the pickup can simply be held in place by hand, or it can be attached with beeswax or double-sided tape. A pickup can also be attached with glue or epoxy. Some pickup devices are equipped with a small magnet that's used to hold them in place. One of the most successful mounting techniques involves bolting the pickup onto the machine being checked. Many pickups are designed with a threaded bolt hole just for this purpose. Unfortunately, nearly every mounting procedure has some limitations. For example, holding the pickup in place can prevent the accurate measurement of higher frequency vibrations, and bolting the pickup onto the machine can be time-consuming. In addition to knowing how to attach the pickup, it's also important to know where to position it. A few general rules apply, regardless of the type of equipment being checked. For example, the pickup should be mounted on the bearing housings or bearing caps. This ensures that the pickup will accurately sense the machine's vibrations, since these vibrations are transmitted from the rotating element through the bearings. The pickup should not be mounted on an unstable surface, such as this label. The label could vibrate more than the bearing housing or cap and interfere with the vibration reading. If the machine being checked has more than one set of bearings, each bearing should be checked if possible. Also, each bearing should be checked from 3 different directions. For example, this horizontal shaft should be checked from a point located parallel to the center line of the shaft, then perpendicular to the center line in the horizontal direction, and finally, perpendicular to the center line in the vertical direction. Checking from these 3 positions will provide all the information necessary. On a machine equipped with a vertical shaft, the readings are still taken from 3 directions. One check is made parallel to the center line of the shaft, another is made perpendicular to the center line in the horizontal direction, and the final check is also made perpendicular to the center line in the horizontal direction, but at a 90-degree angle from the second measurement. The point where the pickup is located on each bearing should be marked so that the same position is used on subsequent readings. If different locations are used each time the machine is checked, the vibration readings may be accurate, but they won't be useful for making comparisons with other readings. Okay, we've seen how the different types of vibration detectors represent an important part of vibration monitoring. But vibration detectors are useless unless they're connected to other testing equipment. When we come back, we'll start looking at some of the devices used to analyze the information provided by the detectors. Pickup devices, like the ones we saw in the last segment, transmit an electrical signal to some type of vibration monitoring instrument. That instrument interprets the signal and provides the technician with information regarding the nature of the vibration. One type of vibration monitoring instrument is a vibration meter. As you recall, vibration meters provide a general reading of displacement, velocity, or acceleration. They normally do not provide detailed information on any of the parameters. However, vibration meters are portable, which gives the user freedom to move from one test point to another. Here's a typical vibration meter. It consists of 3 basic parts: a pickup, like we saw earlier, a connecting cable, and an instrument, which houses the electronic components that convert the pickup signal to a meter reading. This particular unit is battery operated and provides overall vibration readings for displacement, velocity, or acceleration. As you can see, it has a meter and several control switches. The meter itself has scales, each of which has a different range. The scale can be selected according to the amount of vibration being monitored. This switch is used to select the meter scale. There's also an on-off switch. The on-off switch can also be used when testing the batteries. This switch is used to select the parameter to be monitored, either displacement, velocity, or acceleration. There's another setting for this switch labeled SE on this unit that can be used to find faults in roller-type bearings. When the instrument is set at this position, the meter displays the vibration caused by metal-to-metal contact of the bearing components. The meter that you use may be different from the one you just saw. So before you try to use a vibration meter, make sure you're familiar with all the switches and controls. Now let's see how a vibration meter is used. When a vibration meter is used, there are a few basic steps that should be followed to ensure that the readings are accurate. One step is following both the manufacturer's specifications and your own company's procedures regarding the use of the instrument that you have. Another is checking the condition of the instrument prior to its use. The pickup, cable, and meter should be visually inspected for signs of damage. Many of these instruments are powered by batteries, which should be checked before any readings are taken. If the batteries are weak, then it's possible that the readings will not be accurate. After the batteries have been checked, the instrument can be turned on. Many meters have a keypad or switches to turn them on and select specific functions. If the instrument needs to be calibrated, then it should be done at this point. Many instrument manufacturers recommend that meters be calibrated at least once a year to ensure their accuracy. This can be done by using a calibrator, which is commonly referred to as a shaker or shaker table. A calibrator produces a vibration that has a known frequency, displacement, velocity, and acceleration. By placing the meter pickup on the shaker, a meter reading can be taken. That reading can then be checked for accuracy. Once the unit has been calibrated, the parameters can be chosen. In other words, displacement, velocity, or acceleration must be selected, depending on the situation. Then the pickup device can be attached, as we saw earlier. Next, the meter scale should be selected. As I said before, each scale has a different range. Choosing the proper scale depends on which parameter is being monitored. Many meters have a variety of settings to choose from. It's a good idea to choose the highest setting first. Then, if there's little or no needle movement, the meter should be shifted to a lower scale. The same holds true if there's too much needle movement. If the needle is too far to the right side of the scale, then a different scale will have to be chosen before an accurate reading can be taken. Once the unit has been checked and set, the machine's vibrations can be monitored. Now, once the information is collected, it can be used in a number of ways. It can be analyzed by the technician that collected it, or it can simply be given to other personnel for analysis. In many cases, the information is compared with guidelines created by trade groups such as the American Petroleum Institute, the National Electrical Manufacturers Association, and the American National Standards Institute. These guidelines can help determine the general condition of the machine being checked, but may not identify a specific problem. Other guidelines may be available for the equipment in your plant. Some equipment manufacturers supply their own equipment condition guidelines. This information may be included in the operating and maintenance manual supplied with the equipment. It may also be available from the manufacturer on request. Another type of guideline that can be used is a vibration severity chart. A vibration severity chart is a type of graph created from thousands of vibration readings taken from different types of machines under many different conditions. While this type of chart is not a precise indicator, it does offer good general information. By plotting the readings that are taken, the overall condition of a machine can be determined. Let's take a closer look at a section of the chart. The horizontal axis represents the displacement of the vibration, expressed in mils, peak to peak. The vertical axis represents the frequency, expressed in cycles per minute. And the third set of lines represents the severity of the vibration. These lines are normally labeled as good, fair, bad, and very bad, or some similar terms. Each of these diagonal lines also has a velocity value associated with it. To use a vibration severity chart, the frequency is located on the vertical axis on the sides of the chart. A straight line is then drawn across the chart from that point. Next, the measured displacement is found on the horizontal axis at the bottom of the chart. Then a straight line is drawn up from that point. The point at which those two lines intersect will lie somewhere between two of the diagonal vibration severity lines. The area between those vibration severity lines will be marked to indicate whether the condition of the machine is good or bad. A vibration severity chart is helpful when it's used with a meter or analyzer that can be set to measure vibration amplitudes at specific frequencies. For example, the meter being used here indicates a displacement of 1.5 mils at 800 cycles per minute. When the figures are plotted on the severity chart, the lines intersect at a point that falls within the good zone. So at 800 cycles per minute, the vibration is not very severe. Another way to use the chart is by simply plotting velocity. For example, suppose the velocity of the vibration in this machine is found to be 0.1 inches per second. By using only the diagonal lines on the severity chart, we see that 0.1 inches per second falls between the fair and the slightly rough zones. Any machine that is monitored for vibration can have its own graph. That way, each time the machine is monitored, the data that's collected can be plotted on the same graph. Over a period of time, changes in vibration levels or trends may appear. These trends can help maintenance personnel detect problems and schedule maintenance. Well, we've seen how to use one type of vibration instrument, the meter. But meters can only provide general information. Sometimes more specific data is needed. When we come back, we'll look at an instrument that's capable of providing that type of data. In the last segment, we saw how the information from a vibration meter could be used to determine the general condition of a machine. When more detailed information is needed, vibration analyzers are often used. Vibration analyzers are normally used to examine individual frequencies so that more detailed information can be analyzed by the vibration technician or other personnel. As a result, a vibration analyzer can help identify a specific problem. Many analyzers can also be used to balance rotating equipment. Vibration analyzers are available in two basic styles: self-contained units and units that use a computer to analyze the data. There are many variations of these two styles, so the ones that you see here may not be identical to the ones that you'll use. However, they all perform the same basic functions. Here's the analyzer that we'll be using. It's a typical self-contained model consisting of an instrument and a pickup, which is connected to the instrument. The unit is portable and can be powered by batteries or an AC outlet. Like the meter that we saw earlier, this analyzer has several control switches. This switch is used to select the source of power, either battery or AC. This one is used to select the range for the meter. It can also be used to test the meter. In other words, when the switch is set to the test position, the needle on the meter should move to a certain position if the meter is functioning properly. There's also a switch used to select the parameter to be monitored, that is, displacement, velocity, or acceleration. Like the parameter selection switch on the vibration meter that we saw earlier, this switch also has a setting used to detect faults in roller-type bearings. If the switch is set to this position, the analyzer will monitor the metal-to-metal contact inside the bearing. The analyzer also has a function switch, which allows the operator to select overall vibration readings or various filtered readings. When filtered readings are selected, the analyzer examines a certain group of frequencies. This filtered group of frequencies is known as a band. When a band of frequencies is selected for analysis, an analyzer will examine the frequency plus or minus a certain percentage. The total area surrounding the frequency is known as the bandwidth. The function switch on this analyzer can also be used to test the condition of the batteries and to drive a strobe light at specific frequencies. This switch is used to tune in frequencies to be monitored. It can also be used to control the speed at which the strobe light fires. The keypad and the remaining switches allow the operator to control a number of other functions. For example, they can be used to set the unit to take multiple readings, convert the readings from English to metric units, and control the strip chart recorder. However, for our purposes, we'll stick to the basic functions. This analyzer also has a meter that shows the amplitude of the vibration. The meter can also be used for the battery check. Another meter shows the frequency being monitored. If the function switch is set so that an overall reading is examined, then the meter will show the frequency that has the greatest amount of vibration. If a specific frequency is selected, then the meter will show that frequency. On this unit, there's also a digital display, which can be used to show frequency or amplitude. It can also display codes or cues to the operator concerning monitoring problems. All vibration analyzers have specific instructions that should be followed to ensure that the data collected is accurate. For example, certain preliminary steps should be completed before using the unit. First, it should be checked to make sure that it's in good shape. Once the unit has been checked, a parameter, either displacement, velocity, or acceleration, should be selected. This selection may be based on your company's vibration monitoring program or on the speed of the machine being monitored. Usually, velocity is checked first, since it provides an accurate reading of vibration levels over a wide band of frequencies. Once the parameter has been chosen, the frequency band is selected. Here again, it's a good idea to start by measuring the overall vibration level, which is the vibration that's occurring at all frequencies. That gives a good overall picture from which specific frequencies can be chosen and examined if necessary. On this analyzer, both the frequencies to be monitored and the scales for the indicator can be selected. As we saw earlier, it's a good idea to choose the highest indicator scale, then shift to a lower scale as needed. Once the settings have been chosen, the pickup can be positioned at the proper location, and the data can be collected. First, velocity is checked. Here, the analyzer meter shows a peak at a frequency of 1,790 cycles per minute. To get a more detailed look at that particular vibration, a narrower bandwidth can be chosen. The amplitude may have to be adjusted as well. Then, another measurement can be taken. The analyzer then displays the level of vibration at 1,790 cycles per minute, plus or minus a certain percentage, in this case, 5%. Once the amplitude of the vibration is determined, the analyzer can be readjusted as necessary to concentrate on another specific frequency. This process continues until all desired frequencies have been checked and each corresponding vibration level has been noted. To get a printed chart of the reading, the printer function is selected on the analyzer. The analyzer then prints the chart, again with a plus or minus 5% bandwidth. Some analyzers have an adjustable bandwidth, since the size of the bandwidth affects the detail of the chart or graph produced by the analyzer. The smaller the bandwidth, the greater the detail of the chart or graph. As you recall, there are two basic styles of vibration analyzers. We've looked at the self-contained type. Now let's look at the other type, which uses a computer to analyze the data. This type of analyzer normally consists of 4 parts: a battery-powered data collector, which has its own pickup, a computer with software that runs the computer, and a cable that connects the data collector and the computer. To use this type of analyzer, the batteries that power the data collector must first be checked to ensure that they're properly charged. Then, information about the machines to be monitored is loaded into the computer. This information may include the types of machines being monitored, the locations of those machines, and the specific points on those machines where vibration will be monitored. Next, that information is transferred from the computer to the data collector. The data collector and pickup is then disconnected from the computer and taken into the field where the necessary data will be collected. For the most part, all the other data collection procedures used with this type of analyzer are the same as those used with the meters and self-contained analyzers that we saw earlier. After all the information has been collected, the data collector is reconnected to the computer. Then the vibration data is transferred from the data collector to the computer. The computer can then perform the vibration analysis, display the data as a graph on the screen, and store the data and the results of the analysis for later review. In many programs, readings from the same machine collected over a period of time can be compared to see if a trend exists. Okay, we've seen how to use several types of vibration detection devices, and we've seen what can be done with the data that's collected. But there are other important considerations to remember when measuring vibration. For example, there are certain guidelines concerning the way machinery is monitored. When we come back, we'll take a look at some of those guidelines. When vibration data is collected from machinery, the condition of that machinery plays an important role in the accuracy of the readings. In this final segment, we'll concentrate on some of the basic guidelines that need to be considered before and during data collection. Perhaps the most important part of preparing for data collection centers around information known as baseline data. Baseline data describes both the initial information that is collected from new machinery as well as information collected to use for comparisons with future readings. By making comparisons to baseline data, it's possible to determine if a trend exists. In other words, the person responsible for monitoring the condition of the machinery may be able to tell if a fault or condition is getting worse. This information could help maintenance personnel reduce unnecessary equipment downtime. Baseline data should be collected in a number of situations. For example, it should be collected when new machinery is installed. When a vibration monitoring program is started, regardless of the age or general condition of the equipment involved, and before and after any major maintenance or repair on machines covered by a monitoring program. Baseline data taken before repairs can be compared with subsequent readings to determine if the repair affected the vibration. The information will also serve as the new baseline for future readings and comparisons. Since baseline data is so important, it is critical that the operating conditions of the machinery are the same each time vibration testing is performed. If conditions are not matched correctly, the actual vibration of the machine could be masked or exaggerated, and problems could go undetected. There are many parameters that should be checked to ensure that conditions are matched as closely as possible. For example, a machine should be started in accordance with the manufacturer's guidelines or company procedures, and given sufficient time to warm up before the data is collected. That way, the machine should be operating at the proper speed and temperature. The operating speed of the machinery is normally checked, even though it's relatively constant on most machinery. A machine's speed can be determined in a number of ways. For example, most machines have a label plate that lists the speed. Some machines have a permanently mounted tachometer, others do not. In this case, a portable tachometer could be used. When using a portable tachometer, be sure to follow the manufacturer's recommendations for that particular unit. Many vibration analyzers have a built-in strobe-type tachometer that can be used to determine a machine's speed. But remember, when a strobe light flashes at a frequency equal to the speed of the machine will appear stationary, so you'll have to be careful not to forget that the machine is moving. It's sometimes difficult to tell if the strobe light being used is flashing at the correct speed. The machine can also appear stationary if the strobe flashes at a frequency equal to a fraction of the machine's speed, or a whole multiple of the machine's speed. You'll find some additional information about how strobe lights can be used to determine a machine's speed in your text. But to really understand what you're doing when you use a strobe light, you'll have to have some specialized training and practice. Now, another thing that must be checked and matched against the baseline data is equipment load. Equipment load is basically the amount of work that's being done by the machine being monitored. Equipment load is normally checked by looking at meters or gauges connected to the machine. These may be flow rate gauges, discharge pressure gauges, or ammeters. Another condition that should be checked is equipment lineup. Basically, this means that any other equipment associated with the machine being checked must be in the same condition that it was in when the baseline data was collected. For example, suppose these two pumps were operating in parallel when the baseline data was collected. Then, to ensure the accuracy of all subsequent tests, both pumps should be operating in the same manner. Another example of equipment lineup is when two different machines, such as a pump and a turbine, share a common foundation or bed plate. Again, both machines must be in the same condition that they were in during the baseline data testing. Other situations, such as environmental conditions, should also be checked before vibration monitoring takes place. Since extreme changes in temperature can affect vibration, temperatures should be matched as closely as possible to the conditions that were present when the baseline data was collected. It's important to record the conditions that exist when data is collected so that they can be matched for future readings. By matching these conditions, the information collected will be more accurate. That completes our look at vibration. During this program, we saw what vibration is. We defined some of the terms associated with it, and we saw how vibration affects some typical rotating equipment. We also looked at some devices used to detect vibration. And finally, we saw some of the guidelines concerning data collection. By using the information provided in this program, you should be able to accurately measure vibration on the machinery in your plant. When you do, you'll find that a great deal of information can be obtained. Information that can save you time and effort.